Many of us share this memory, dipping a plastic wand into a soapy solution and launching a cluster of bubbles into the air. There is a consistent geometry at work here. Regardless of how liquids are splashed, sprayed, or blown, free-falling drops and bubbles naturally settle into spheres. This occurs because of surface energy. Molecules in the bulk of a liquid are pulled in every direction by their neighbors. However, molecules at the air interface lack neighbors on one side. This imbalance gives surface molecules an excess of potential energy. As shown in this comparison, a liquid adjusts its geometry to reach the lowest possible energy state. For any fixed volume, the sphere is the shape with the absolute minimum surface area. While this shape minimizes energy, it creates a mechanical side effect. The surface acts as a stretched elastic skin, exerting a constant inward pull on the liquid within. Every droplet functions as a pressurized vessel. Because the surface molecules pull inward, they create a sustained compression that must be countered to maintain the drop's size. If the surface tension is constantly pulling inward to shrink the droplet, we must account for why the drop does not collapse entirely. The structure is maintained by the outward pressure of the fluid trapped inside the sphere. Calculating the stability of a drop requires measuring two variables. We look at the surface tension pulling the skin tight and the pressure difference between the internal fluid and the external atmosphere. A stable drop exists in a state of precise equilibrium. Its shape is the result of the internal pressure exactly offsetting the inward pull of the surface. To find the values for this equilibrium, we can start with a schematic of a solid liquid drop with a radius r. Consider a hypothetical expansion where the radius increases by a microscopic amount, which we will label delta r. Increasing the surface area requires an energy investment. The cost for this extra surface is calculated as 8 pi r times delta r times the surface tension. To force this expansion against the tension of the surface, the internal pressure must perform work. That work is defined as the pressure difference multiplied by the change in the sphere's volume. In a stable drop, the energy required to stretch the surface must exactly equal the work performed by the internal pressure. This balance requires the pressure inside the drop to be higher than the pressure of the surrounding atmosphere. When we simplify that equation, we find that the excess pressure equals 2 times the surface tension divided by the radius. This establishes a consistent rule for fluid interfaces. The concave side of a curved liquid surface always maintains a higher pressure than the convex side. We can apply this rule to the inverse scenario, a spherical pocket of air trapped inside a larger body of water. Because this cavity still involves a single boundary between liquid and gas, the same ratio of 2s over r dictates the internal pressure. Whether it is a drop of water in the air or a bubble of air in the water, the presence of a single interface generates a predictable pressure difference. However, the soap bubbles we blow through a wand have a different physical structure than the solid drops we just measured. This microscopic cross-section shows the bubble's architecture, a thin liquid film with empty space inside and out. Therefore, air meets the liquid on both its internal and external surfaces. With two distinct liquid-air interfaces, the inward pull from surface tension is doubled. To counteract this, internal pressure must be higher, shifting the excess pressure formula to 4 times surface tension divided by radius. This comparison highlights the difference. A solid water drop requires half the excess pressure of a hollow soap bubble of the same size. This doubled interface explains the effort required to blow a soap bubble. You must provide enough internal air pressure to counteract the tension of both surfaces simultaneously. What begins as a simple breath becomes a demonstration of the precise balance between pressure and surface energy.